Hello everyone, myself I'm K. Salomi Rani from the Department of Physics, working as an assistant professor in Marri Laxman Reddy Institute of Technology and Management. So today I'm going to explain a very basic topic, so that is magnetic material. So in this lecture we are going to discuss basic definitions and types of magnetic materials. So in the universe, there are so many types of materials are there. So in that, we can differentiate the materials are magnetic and non-magnetic materials. Does all the materials are magnetic? Means no. All the materials are not a magnetic materials. So there is a magnetic and non-magnetic material. So behavior of the response of the magnetic field applied to the materials, we can classify the materials are magnetic and non-magnetic materials. So how the material can be classified as a magnetic material means, if the material is having the magnetic momentum, so that type of materials are called the magnetic materials. How the magnetism of the material is arises, it is completely depends upon the spin momentum and angular momentum of the atom in a material. If the spin angular momentum combination, so what we gives us the resultant magnetic momentum of the material. If the magnetic momentum of the material is not equal to 0, so that type of materials are called the magnetic materials. So here it is a few lines introduction about the magnetic materials. So all the material can be magnified, all the materials can be magnetized in the external magnetic field. The magnetic materials can be magnetized by applying the external field to the material, by induced the magnetic field, or by creating the permanent magnetic momentum inside the material. The magnetism arises from the materials due to the dipole momentum or magnetic momentum created inside the material by applying the external field. So here different types of magnetic materials in this picture you can see. So bar magnet, ring magnet, shoe horse magnet, so magnetic compass. So these are the different types of magnets. Every magnet having two poles. So that two poles are called north pole and south pole. So every magnet having two poles that are called the north pole and south pole. Both are having the pole strength, but they are having the opposite polarity. So that is called the dipole. So every magnet is having the dipole, and that dipoles are having the dipole momentum. So what is the dipole? So dipole is a separation between the two poles with a particular distance. So every magnet is having the dipoles. So north pole and south pole is here separated with a particular distance. So coming to the bar magnets, the dipole momentum and dipole of the bar magnet is you can see in the picture. Here we are considering the one bar magnet, so which is separated with a north pole and south pole with a particular distance 2L. So the magnetic momentum of the dipole is indicating with, so m is equal to distance of the bar magnet and multiplying with a pole strength. So here we are considering another magnet, so that is the ring magnet, so which is indicating in the figure, or nothing but a current carrying loop. So that is also having the magnetic momentum. So that magnetic momentum is depends upon the current carrying in the conductor and the product of the area of the ring. So next one is the magnetic field. So every magnet is having the magnetic field. So what is the magnetic field? The magnetic field is area surrounded by the magnet. The field lines are spread over the magnet. So that area is called the magnetic field. The field lines are indicating from north direction to south direction. So next one is the magnetization or intensity of magnetization. So what is the magnetization? The magnetization is a property of converting non-magnetic material into magnetic material. How the magnetic materials are created? By this process. So here we are converting the non-magnetic material into magnetic material by applying external field to that materials. When we are placing a material in a external field, so that material can be converted by external field into a magnetic material by producing dipoles inside the material. So because of that dipoles, there is a magnetic momentum inside the material. If the resultant magnetic momentum is not equal to 0, that type of materials are called magnetic materials. Like this, the materials are magnified. So the intensity of magnetization is how much degree of magnetization happens in a materials. which indicating the intensity of magnetization. So this intensity of magnetization, so we can represent with capital I here. So that is proportional to the magnetic momentum per unit volume. If you consider any material, we are placing in external magnetic field. So how much magnetization happens in a material? So we can consider here. So in a particular volume, how much magnetization in that materials? We can describe the intensity of that magnetization of material. So next definition is magnetic flux density, capital B. So before going to know about that magnetic flux density, we should know about the magnetic flux. What is the magnetic flux? The number of lines passing through a surface area for any magnetic materials. Here you can see in the picture, so we are considering area A, the magnetic lines are passing through the surface. What is the magnetic flux? The magnetic flux is, if you consider a particular area, so in that area, how many lines are presenting in that area? So that is called the magnetic flux density. So here we are indicating the magnetic flux with capital B. So capital B is proportional to the magnetic lines which are passing through the magnetic lines which are passing through the surface area. So here that magnetic lines passing through the area is phi by A. So phi is the magnetic flux. The number of lines per unit area is indicating the magnetic flux. So we can remember like this also. The induced magnetic field inside the material also we can call it as a magnetic flux density. So because of that external field we are applied to the material, there is a field inside created by the external field. So that induced field also we can remember like this, capital B. Next one is the magnetic permeability. So what is the magnetic permeability? The magnetic permeability is the capacity of accepting nature of the magnetization of the material. How much degrees there is a magnetization happens in a material. So it is depends upon the external field which we are applying to the material. If we are applying the here, external field is capital H. So that capital field is that magnetic field is proportional to the induced field in the magnetic material. So here the induced field or induced magnetic momentum is capital B. So that capital B is proportional to the capital H. So here the proportionality constant we are taking as a mu. So this mu is the magnetic permeability of the substance. So this magnetic permeability of the substance we can write the ratio between the induced magnetic field induction inside the material by the applied external magnetic field. So this is the ratio. So we can remember like this, the ratio between the induced magnetic field and applied magnetic field. So next one is magnetic field strength or magnetic intensity. The magnetic field strength is at any point in the magnetic field is the force experienced by the north pole. So how many lines are experienced from the north pole? So that can be, we can say, the magnetic field intensity. So next definition is magnetic susceptibility. So the magnetic susceptibility is the ratio of intensity of magnetization because of that external field which we are applying to the material. So completely the susceptibility of the material is depends upon the intensity of the magnetization and applied magnetic field to that material. So next one we are going to discuss about the classification of different types of magnetic materials. There are so many types of magnetic materials are there. So in our syllabus we have 5 magnetic materials. So they are diamagnetic material, paramagnetic material and ferromagnetic material, antiferromagnetic material, ferrimagnetic materials are ferrites. So first one, so here what is diamagnetic materials? So when we are placing any material in the external field, so it is show different types of properties. Depends upon that properties we can classify the material is belonging to the which type. So whether it is going to a diamagnetic or paramagnetic or ferromagnetic or other than. So here diamagnetic materials are the materials which are repelled by the external field. So if we are applying the external field to a material, so that materials there is a dipoles created, but that dipoles are created in opposite direction. So because of that anti-parallel manner, that materials are repelled by the external field. So these type of materials are called the diamagnetic materials, the materials which are repelled by the external magnetic field. So here some are examples for the materials. So that is graphite, bismuth, lead, mercury and etc. So in this picture you can see the, so before applying field, so there is no dipoles created in the material. So they are, so no dipoles. So when H is equal to 0. So after applying H is not equal to 0 means, so after applying the field, external field to the materials, there is a creation of magnetic field inside the materials. So because of that external field, the dipoles are produced, but they are in opposite direction. The dipoles are created in this direction. We are applying field in this direction. So these dipoles are anti-parallel manner. So because of this anti-parallel manner, so these dipoles are repelled by the external field. So here it is, some are the properties for the diamagnetic material. So the diamagnetic materials are repelled by the external field lines which we are applying to the material. We are applying the external field to the material. So that material is repelled by the external field lines. So second one is, because of the opposite field lines, there is no permanent magnetic momentum inside the material. Susceptibility of the material is negative and it is independent of the temperature. So whatever may be the temperature, the susceptibility value is negative. There is no changing in the susceptibility value. What is the permeability? So permeability is the, here the relative permeability of the material is very less. So which is less than unity. Here you can write the permeability is mu r. So what is the permeability? So permeability is the relation between the, so mu r is equal to permeability of the material by permeability of the free space. So here the relative permeability indicating the, so relation between the, or ratio between the permeability of the substance and permeability of the vacuum or free space. Here the relative permeability value is unit, less than unity means less than 1. So next one, the spin alignment of the all the dipoles in anti-parallel manner or randomly. So you can see in the picture. So if you draw the graph between relative susceptibility and temperature, so this is susceptibility and the temperature T on x-axis. So you are getting negative susceptibility, means you are getting the, so like this, the graph is looking like this. So this is the indication for susceptibility and temperature. So next one is the paramagnetic materials. Here the paramagnetic materials are which are weakly attracted by the external field. So when we are applying the external field to the paramagnetic materials, they are weakly attracted by the field. So that type of materials are called paramagnetic materials. Here some are example for the paramagnetic materials: lithium, magnesium, molybdenum and tantalum. So these are the examples for the paramagnetic. So here you can see the, before applying the field, the dipoles are in random manners. So here you can see after applying the field, the dipoles are created, but all are not parallel to the field. So here the field is in this direction. The dipoles are not exactly parallel to the field which we are applying. So that's why there is a magnetic momentum inside the substance, but which is not a strong magnetic momentum or more magnetic momentum. So very less magnetic momentum. The resultant magnetic momentum of the material is very less. So this type of materials which we are weakly attracted by the external field, they are called the paramagnetic material. So here it is a sum of properties of the paramagnetic materials. The paramagnetic materials attract the magnetic field lines weakly. There is a permanent magnetic momentum, but which is very less value. Next, the susceptibility of the material is positive and which is independent of the temperature. The permeability or relative permeability of the material is greater than 1. So means mu r is greater than 1. The spin alignment of the dipoles is random manner. So if you draw the graph between susceptibility and temperature. You can observe here at low temperatures, the susceptibility value is high. If you increase the temperature, the susceptibility value will be decreasing. So this is the graph susceptibility and temperature, which we are indicating in the figure. So next one is the ferromagnetic material. Here the ferromagnetic materials are the materials which are strongly attracted by the external field. So when we are applying external field to the materials, that type of materials are strongly attracted by the field. So why they are strongly attracted? So the dipoles which are created inside the materials all are parallel to the field direction. So all the dipoles are in parallel manner. So because of this, there is a resultant magnetic momentum inside the materials which is very high. So because of that more magnetic momentum inside the materials, they are strongly attracted by the field. The best example of ferromagnetic materials is nickel, copper, iron and all the alloys. Here you can see the before applying the field, there are dipoles, and after applying the field, the dipoles all are aligned in the field direction. All the dipoles are in field direction. So H is not equal to 0. So because of this parallel manner, so all the dipoles which are in a field direction are alignment in the field manner. So there is a permanent magnetic momentum. So this permanent magnetic momentum happens after removing the field also. So this is the major property of the ferromagnetic materials. After removing the field or in the absence of field also, there is a remainsness of the magnetic nature inside the materials. So that is the main property of the ferromagnetic material. So here you can see some of the properties of the ferromagnetic field. So all the dipoles are aligned in the parallel manner to the applied field. So next one, they have the permanent and strong magnetic momentum of the material. So it exhibits the magnetization even in the absence of the field also. So the relative permeability of the material is very much greater than unity. So that is mu r is greater than 1. So next one is they exhibits the hysteresis curve. So what is this hysteresis curve? So it is a loop which indicating the converting the non-magnetic material into magnetic materials. So that closed loop is called the hysteresis loop. It is a process of converting non-magnetic material into magnetic material. How it happens? It will be shown in a closed loop. So that is called the hysteresis curve or hysteresis loop. The susceptibility of the material is very high and it depends upon the temperature. If you draw the graph between susceptibility and temperature, here you can see if the temperature is increasing, the susceptibility of the material will be decreasing. So initially the susceptibility is high, the temperature is increasing, susceptibility value will be decreasing. So next type of materials are antiferromagnetic materials. So antiferromagnetic materials also one of the type of ferromagnetic materials. So in these materials, the spin alignment is anti-parallel manner. So completely the dipoles are in anti-parallel manner with neighboring dipoles. Because of that, due to unfavorable exchange of spin alignment inside the many. So unfavorable exchange of interactions among them. So resultant of this, there is no magnetic momentum inside the material. Why? Because here the spins are in opposite direction. So one is in lower direction. One spin is in positive and another one is the negative. So because of all spins are cancelled, the resultant magnetic momentum is 0. So there is no magnetic momentum inside the material. So but the antiferromagnetic materials which exhibits a small positive susceptibility. There is a susceptibility value although the magnetic momentum is 0. When the susceptibility value is high, the temperature of the material is increasing. At particular temperature, the susceptibility value will be maximum. So that type of temperature is called Nil temperature. So Nil temperature is a particular temperature where the susceptibility of the antiferromagnetic materials are maximum. After increasing the temperature, Nil temperature, above the Nil temperature, they will be act as a paramagnetic materials, means the susceptibility value will be decreasing. Again, you are increasing the temperature. So here you can see the picture, the susceptibility of the material, how it will be changed. So initially the susceptibility of the material is 0. At particular temperature, it is getting maximum. So this temperature is called Tn, Nil temperature. So after this temperature, if you are increasing the temperature, the susceptibility value will be decreasing. So this temperature is called the Nil temperature. So coming to the properties, the electron spin of the neighbor atoms are aligned antiparallel. So here the spin alignment is antiparallel with neighboring atoms. So this is the spin manner. Antiferromagnetic material susceptibility is completely depends upon the temperature. Here the temperature is major roles, the temperature plays major role in the susceptibility value. Here the temperature is increasing, the susceptibility increasing, after getting maximum it will be decreasing. So next one is the here. So next one, ferrimagnetic materials. Ferrimagnetic materials also one of the ferromagnetic material type. Ferrimagnetic materials which are similar to the ferromagnet. So in this ferrimagnetic materials, the spin alignment is antiparallel in manner but with unequal magnitude. So here if you are observing, so these two are in antiparallel, but the magnitude of both is not same. So because of this unequal magnitudes, there is a magnetic momentum inside the material. So because of this magnetic momentum, if you are applying any weak field to the materials, there is a large magnetization produced inside the material. So this type of materials are called ferrimagnetic materials. So here it is some of the properties for ferrimagnetic material. So ferrimagnetic materials are magnetic momentum is not equal to 0. So in these materials there is a magnetic momentum, so which is not equal to 0. So at a particular temperature it will be act as a paramagnetic materials. Below the temperature it will be act as a ferromagnetic material. It shows two types of properties. So here, so this is the temperature. So above this temperature they will act as a ferro. So below this temperature they will act as a para. So this temperature is called the Curie temperature. The spin alignment is antiparallel with different magnitudes. So the susceptibility of the material is very large and positive. So it is completely depends upon the temperature. So they have high permeability and resistivity. So here you can see the graph which is indicating the susceptibility of the material with the temperature, how the susceptibility will be changing with the temperature, you can see in the picture. So in this graph we can observe, so all the materials, how the susceptibility of the material will be changed with the temperature. So first one, so this is the diamagnetic materials. So next one is paramagnetic materials, and third one is, this one is ferro, ferrite and antiferro. All these materials, how the susceptibility value will be changing with the temperature, you can see in this graph. So last one, so this flow chart can indicating the, it is very helpful. So by seeing the flow chart you can understanding how the dipoles are formed, so how the dipoles are behaving, so what is the susceptibility value, what is the direction of dipoles, all these you can see in this picture. So thank you, Ananda.